Yeah, so last time we were doing differential forms. We talked a little bit about tensors and stuff. Let's see. I mentioned that D thing, the exterior derivative, is differentiating zero forms. But what does that really mean, right? You probably have like solved differential equations where you had to do something like taking the total derivative. Right? So you take some function x, y, z, and you take exterior derivative of that, and you get a line integral, something like that. You get a one form. But what is that really doing? Let's look at how we might visualize that. So if you've got, let me think of how to do this. If you've got a function m mapping to n, call this f, and it's a smooth map. M and n are both smooth manifolds. Namely, this is dimension m, this is dimension n, so we have this property. Just distinguishing the dimensions of each of these manifolds. Then what you have as the, yes, okay, so last time when I talked about taking exterior derivatives of zero forms, I did maps from M to R, not from M to N, just a generic manifold or anything. So this is, in general, you can take any manifold, and you can take the exterior derivative of a zero form, or a smooth function. And what that looks like is you'll have Tm mapped over to Tn by df. And the idea is that this should commute. This diagram should commute. So this takes a tangent vector to m and maps it to the point at which the vectors of the tangent, in the tangent space of, maps it up to here, and then if you go over here through the map f, that's the same as having mapped through the differential map and then going up to n. But that's not really the interesting part. What's going on? Okay, so let's draw a little picture. Let's say I've got a map from R2 to R2. It might look a little patch of R2, and it might look something like this, and you might have a coordinate system. So you got two tangent vectors here at this point. And F maps you over to here. Another copy of R2, and I'm just looking at a little coordinate system on it. And you've got your coordinate system here. Now, you can look at what happens if you take the x coordinate, that coordinate curve where y equals 0, and you map it. So this is, let's say, capital X equals everything in R2. So where you have x and 0 in R2 on the set. And you map that over to here, and depending on what f is, you can get any kind of curve. It might be up here. This might be f of x. Okay. So what is df going to do? Well, to this point, df should eat tangent vectors, right? So I should be able to take, let's see, I should be able to look at the tangent spaces. So I should be able to look at this point, look at its tangent space, and you have a basis put on here by the coordinates in R2. So you have x, you have y. This is del x, del y in this case. This is del x, del y, and this is the tangent space to 0, 0 in R2. And these tangent vectors in here should be mapped over to here in some natural way. Now the idea is that f maps you from 0, 0 over to this point, and so we should have df being a map from this tangent space to 0, 0 to the image of 0, 0 over here. So you have f of 0, 0 right there. And you have its tangent space. Now, you might even look at it this way. It should be really a square, not a diamond rotated like that. Okay. And you have a coordinate system imbued on this by the fact that this point lives in R2. And it looks like this. Okay. So let's draw that here. This is again del x, del y. This lives in the tangent space to f, 0, 0 in this copy of R2. Now, where should these tangent vectors map to over here by df? Well, you just look at the function itself. You say, okay, well, I take this and I walk in this direction a little bit, and if I do that over here, then what's going to happen when I map points successively as I walk that way through f is I'm going to walk along this curve a little bit. If you walk a very short distance, you're going to go in this direction, tangent to the curve. And so naturally, that direction, you just project onto the tangent basis, and you get this vector. And so df is always a linear map. Okay? Always. And quite literally, if I defined what f was, I would be able to just take the exterior derivative of f manually, right? So df is always equal, in this case, to f differentiated with respect to x, dx, plus f differentiated with respect to y, dy. And you can just plug in a tangent vector here to this thing. Put in the point at which you're tangent to, and it will tell you what the image is here. So that's what we're doing algebraically when we calculate the exterior derivative. So we're figuring out how the tangent vectors, infinitesimally, what does walking along them look like over here in the image space. So that's the geometric interpretation of the exterior derivative of a zero form. Same thing, no matter, you might have this mapping from R2 to R3 or just R2 to R, doesn't matter. It's always going to be the same interpretation. It's a linear map, always. And you can write it as a matrix if you like. Whatever. Let's see. So, what is a differential form talking about? What is the point of it? The origin was that they wanted to generalize, differential geometers wanted to generalize integration to arbitrary manifolds, and it kind of works this way. So give me some integral, like maybe on R2, the function might have an integrate.
X squared y.
Okay. Dx. Now, you can pick out any region of integration you'd like to integrate this on. So usually they write R here, not like real numbers, but just some region in R2, or a domain even. And you're free to choose that, and then you don't have to redefine this thing. Now this looks kind of like a differential form. And it turns out that the way you define this is you write the same thing, but you put a wedge between each of the differential one forms, the basis points. And sometimes the convention is that people will write D here, and it just means the same area in R2. So let's say, like, I've got, in R2, I've got some kind of patch. I can integrate this function over this patch. And it's pretty easy to do so because I just come up with some parameterization of the patch, and then I do integration along x only, and then y only. It's easy. But the trouble is, if I were to commute this, this would become negative. So that's x squared y dy wedge dx. Okay. But this would not become negative if I commuted. Right? Keep the value the same. So why is that? The idea is, when you write D here, you're taking an orientation for D. You kind of implicitly state that you're going to take the counterclockwise orientation. R2. If you're working in R1 and you're not on a closed curve, if you're on a closed curve, you just go counterclockwise. But if you are doing just a line integral, you have to actually say where the start and end is to pick an orientation. Differential forms have this built in by nature of the algebra, right? If you commute the components of the wedge product, it anti-commutes, so it becomes negative. So they have a natural inbuilt orientation. The idea is this. You use the right-hand rule always. So if you write dx, dy, you can think of having written x tangent vector in that direction, and then y like this. So this is del x, del y. And then making a parallelogram. And then you put x first, so you go in that direction to start with, and then you just keep going around the parallelogram. And you get this orientation, counterclockwise. Okay? So if I had written dy first, I would go the other way. This works for 3 forms as well. You just get oriented parallelepipeds. And the idea is whatever region of integration you're talking about inherits the orientation from the way you write the differential form. So if I wrote dy wedge dx, that would be this orientation, the clockwise one. So the order you write your differential form in determines the orientation. You don't pre-select it when you choose the region. Also, I should say, if you write something like this, where this is a differential form, the orientation is chosen, the domain of this thing is chosen, right? Because you have it being a differential form on some manifold, and this integration is over the whole manifold, so you don't really need to even write D. There's no such thing as anti-differentiation with differential forms. You're just actually integrating, taking the definite integrals. So that's how you differentiate. I mean, it's pretty natural. Just choose an orientation that's obvious from your wedge direction, and then you just integrate like normal. We haven't really gotten any new tool. Okay. Let's see. So there is an example I give, which is that we want to put a differential one form on R2. So say alpha is equal to, what did I put? Negative y dx plus 2x dy. Okay. And we want to integrate this. So this is a differential form on R2. And I'd like to imagine what this looks like. Right? So it's some kind of swirling vector field. And it looks, let's do this in a different color. It looks like this. It's not exactly a circular flow. Let's see. You end up going horizontally when you're on this axis, but you kind of go faster downward and then upward in this direction. So you have outward vertical flows are a little bit faster than circular. So this is what that form looks like. Right, you can see it's faster in the vertical direction. And then we would like to integrate this vector field on S1, which I'm defining to be just xy in R2, such that x squared plus y squared equals 1, the unit circle. Okay. So I want to integrate alpha on S1. Okay. How would you do this? Well, my definition so far doesn't really allow me to do this without, thinking of how to do line integrals in general. You can draw what this looks like. It's just this, and this has an orientation not picked out right. hasn't inherited from the basis to form the volume form on R2, which is dx wedge dy. So it gets this counterclockwise orientation on it. Okay. So to take this differential one form defined on R2 and leverage that to integrate on some submanifold of R2, I need to define what's called a pullback. So I need to pull back that differential form by some function. Let me see the computation real quick. Okay, so we have a parameterization of the circle, gt, and it's defined this way: cosine t sine t. Now I'd like to define something called the pullback of the differential form alpha by g. We write g star alpha. And this should be a differential one form on not R2 anymore, but on S1, on the image of G. So you might write S1, or you might write G of R. Okay. Parameterization. So the image of that parameterization. Now, this thing is defined in such a way to satisfy this property. If I take a tangent vector to S1, so let's see, I might write B, that's going to be equal to alpha composed dg of B. So what does dg do? It takes tangent vectors to R, right? Or rather to S1, and it maps them over to tangent vectors to R2. And you can imagine that if I took in some abstract space a tangent vector to S1, it would look like this. Well, it's just going to map straight to this in R2. The same point where we're living. Okay. How do you actually compute that? Well, let's do this. G star alpha is just a precomposition in some sense like this. So I need to compute, this is going to be kind of thing. We're going to get a differential one form on S1. So it should be in terms of the parameter t. Okay. So let me see the computation again. After you do it once, get comfortable with it, but okay. Let's pull back something other than alpha real quick, which is just dx. So g star, remember I pulled back a differential form of dx is going to be d, and then you take x and you just plug in whatever x is here. This is x for us, this is y. D cosine t, which is negative sine t dt. Easy. The pullback of dy would have been d of, I should say, this should have been x gt, like this. So this would be y with gt in it. This is the selector function for the y coordinate. So you get d sine t, which is cosine t dt. Okay.
Are we working from a definition for pullback here, or just?
Sorry?
Are we working from a definition for pullback here?
Yes. This definition.
Okay.
And I've kind of fudged this a little bit. It's a little bit strange. I think it should have a d here, but what you do is you take the coordinates and you just stub in the stuff. Right?
Yeah.
So I've got g, which is this. I want to know what g pullback dx is. Well, I just replace x with whatever the x coordinate of g is. It's like a precomposition. So then now I can pull back this alpha. So G star alpha is going to be, well, that's going to have been negative G star to the pullback x linearly, y dx, plus G star x dy. Right, so I'm getting that from the definition of alpha over there. 2, sorry. And now I just precompose. So what is y? It's sine t. What is dx? Well, I already computed that. That's sine t. So sine squared t now, dt. Plus 2. And then you'll get cosine squared t dt. And that's all you can simplify by. We can do that right. Yes. Oh, you can, I did something a little bit stupid, which is that this was supposed to have had another negative in it because of this. So that would have been like this, so then we can simplify and we just get dt plus cosine squared t. So that should be 1 plus cosine squared t dt, because I had another copy of cosine squared t dt right there. Now, the idea is if you've got, how does this work? This theorem's a little technical. So proposition. Let U and Rn be a region. That means, you know, an open set, or like at least part of a closure of an open set. And let G be a function from U to Rn, which is smooth. And it has to be a one-to-one map, and it has to satisfy the following condition. The determinant of the Jacobian of G must be 0 everywhere except on a measure 0 set. But these are just technical things. In practice, you just compute the thing, and it is easy. Basically, I mean, if you take a parameterization of a submanifold of Rn, that's G. And it should be a full dimension submanifold. And then you say, okay, if omega is a differential inform defined on S, which is equal to G of U, so the image, like the manifold that you're parameterizing, then you have the following. The integration on S, that parameterized submanifold of Rn, like the circle, well, I'm not doing a circle, but we might have like a disk in R2 or something. That would be S. Then you have this property. The integration of that differential 2 form on it is equal to the pullback of the parameterization, or pullback of the differential form by the parameterization on the whole domain. Okay. And you can generalize this and say the following. Because we want to do it for submanifolds of a different dimension than the whole space that they're embedded in. Okay. So if you have the following, if you have U is in Rk, so this K may be different than N. So you know, if in our case we have this being a parameterization of the circle, so it's going to be R1. And G, mapping from U, which is the parameterization, over to Rn is smooth. Okay. also have the criterion on the Jacobian being that it has to be full rank everywhere on U. So this should equal K on U. What that means is that your parameterization doesn't fold over on itself or anything. Except on measure zero set, then we say that M, which is equal to G of U, is a parameterized K manifold living in Rn. And you have the following property. If you have a differential inform, or even a K form actually, you have a differential K form living in Rn, and you want to integrate it on M, that parameterized submanifold, the integration of it on there is equal to pullback by the parameterization on all of the parameter space. So let's actually compute with this now. That's the full proposition that you need to do calculations on submanifolds. So remember, this is our pullback. In practice, using it's much easier than writing out the propositions and stuff. Okay, so what are we trying to do? We're trying to integrate on S1 differential form alpha. Okay, so this is a parameterized submanifold of R2. So we've got the setup that we have over there, right? This is M. U for us is going to be something like 0 to 2 pi. Because think of our parameterization, it's cosine t, sine t. So we want to go full revolution. So we go 0 to 2 pi. And this has the orientation, which is just 0 to 2 pi to the right on the real number line. And let's see, I want to integrate the pullback there, and that's this. You can now write it in the classical way, which is like this. Okay. So that's your integration. And you can just compute this using elementary integration. I kind of want to show how you would integrate this with the knowledge of exterior derivatives and differential forms, because it changes how you do it from Calc 2. It's a little bit different. So how would we get the antiderivative of this thing? Well, firstly, you use the linearity of integration. And you say, okay, well, this is going to be 1 dt plus integration cosine squared t dt, okay, like usual. This you know. The integration of dt, the antiderivative, is just t plus c. And then you have this thing left over. But I can simplify this using the power reducing formula. So that ends up being 1 plus cosine 2t over 2 dt. You have a constant still in here, so I still don't need to write plus c just yet. And I'll come up here. And I have some trouble. I can use linearity again, and I can get t plus t over 2 plus this thing now, 1/2 cosine 2t dt. And this one isn't the greatest example, because it's just kind of obvious that d 2t I would like to have. And what is this if you differentiate with respect to 2t? Or with respect to t, you get 2 times dt. And you can just divide by 2 on both sides. And then this is easy to solve. So 3t over 2, combining these two, plus 1/2. And then you have
cosine 2t dt 2t. Then you had another factor of 1/2 come out, so that, and then this is just the usual. In general, though, if you have, let's see, if you have something like this, sine t, cosine t, dt, when you do u substitution, you're looking at this to be the derivative of this thing. And what you can do is you can notice that this is a differential one form. And in some sense, you can think like, okay, I can integrate this thing into the exterior derivative and just think of taking that, like, and integrating it and sticking it inside of here. And then you don't have to write out like u equals sine t, du equals cosine t dt and all this stuff. But it just makes it a little bit easier to think, okay, this is now sine t, d, sine t. And just working with differential forms, everything becomes a little bit more lubricated and you can solve integrals like 50 times faster.
So when it comes to applying the bounds, do we always just sort of apply the bounds at the end and then like
And calculate the number that comes out?
yeah.
You'll always get a classical integral, except when you use the thing I'm about to show, yes, which is kind of the biggest result in differential forms, the Stokes theorem. So you can use that a lot of times, and it will just give you a result instantly. You don't have to do this. But yeah, if you're just using the pullback, in general, you're going to end up doing this thing.
Yeah, okay.
You'll have a classical integral at the end. And you get 3t over 2 plus, whatever, plus 1 over 4 sine t plus c.
0.
Yeah, and then you apply it fundamental thermic calculus. And so that's what this integral ends up being. Not 0. Oh, see?
The total thing should be 0.
No,
Then we integrate around the loop.
this doesn't get killed. It'll be 2t. It'll be 6 pi. No, 3 pi, sorry. 3 times 2 pi divided by 2 gives you 3 pi. Minus 3 times 0.
Okay,
Yeah. But this part, yes, that gets killed. All right, now the big, that's how you compute the pullbacks. You said, how you integrate on submanifolds of R. You just take the differential form that you want to integrate, you come up with a parameterization for the submanifold, you pull back that differential form by the parameterization,
Yeah.
and then you integrate in the parameterization space of the submanifold. So that works in general. No matter how curvy, how weird the submanifold is, as long as your parameterization is non-singular everywhere except on a measure 0 set, you're good. And measure 0 because measure 0 sets don't change the integral. Right? You know that in general. If you're doing integration of an area and you're 0 on some line, it's the same as if you're 50 on that line. It doesn't change the integral. So Stokes' theorem is this. Exactly right. I have a bunch of exercises for computing the pullbacks and stuff. But here we go. This is generalized Stokes theorem. Let M be a compact, I think. Compact, oriented, smooth. So it can't be unbounded. And it is an n-manifold with some kind of boundary, maybe no boundary, but we'll, restrain anything satisfying this. Let omega be an n-1 form defined on, let's see, on M.
not be that. Oh yeah, it should be. In minus 1 form, phi on m. Then you have this property. The integration on on the boundary of m of omega, because think you don't really want to integrate this thing on all of m because it's one less dimension form, so it's trying to measure hypervolumes or hyper areas in the manifold. So if you're working in R3, m is a 3 manifold like R3, then omega is going to be in area form, or some kind of 2 form. So it'll measure areas. But this thing is equal to this. So what does this say? If you want to integrate a manifold on the boundary, a form on the boundary of something, just integrate the exterior derivative on the interior. So you just move this d operator up here, and it gives you the same result. Okay, what are some applications of this? Corollary 1 is fundamental theorem of calculus, follows from this. Corollary 2, Green's theorem follows from this. 3, Stokes' theorem, when you integrate on a surface, if you integrate on a volume, it's the same as integrating around the boundary. That's also a corollary of this. And then the Gauss theorem from electromagnetism is also a corollary. Okay. So how exactly does this look? Because I say that it's the same thing as fundamental theorem of calculus, but what does it actually mean? It means this. If I've got a one manifold and it's oriented, and I want to integrate the differential form, so this would be I'm integrating on m, the differential form omega exterior differentiated. Then all I have to do is I say, okay, well, let's actually do this one. So give me, let's see, I want to do 0 to 1, and I want to do x squared dx. I want to integrate this using Stokes' theorem. Imagine the middle one. Here's 0, here's 1. I'm just integrating over this form. So I want to know what omega should be. In this case, this whole thing is d omega for us. What should omega be? Right, so think if omega is a 0 form, then omega is equal to f of x, right, smooth function on the rotary line. And so d omega should be f prime of x dx. And so f prime is x squared, so that f has to be equal to x cubed over 3 plus some constant. So what I want to do is I want to say that this is equal now to omega on the boundary of this thing. And the boundary of this is just, well, this is oriented, right? I'm going that way. And we think of this being a discrete set of just this point and this point, where we put a positive orientation on this and a negative orientation on that. And because you're integrating 2 points only with a 0 form, it just eats those points and acts like a sum. So it ends up literally being 1 cubed over 3 plus c minus 0 cubed over 3 plus c. And you get the usual thing. So when we do Differential Topology, every time we try to compute an integral, we're going to need Stokes' theorem. Because it's very hard to think of what integration looks like in dimension 50. And Stokes' theorem is going to allow us to do it algebraically. There's another operator that I kind of wanted to show, which is what exercises are. I don't think I do. The Hodge star. So the Hodge star acts like this. If you have a differential form, let's say you're working in R2, and you take dx, for example. The Hodge star is going to give you another differential form. So if you're in R2 and you take a differential 1 form in Hodge star, you're going to get a 2 minus 1 form, which is just a 1 form. And the idea is that dx wedge its dual star should give you a volume form, which is just the basis in form. If you're in R2, it's going to be the 2 form with all the components. Okay. So what should star dx be in this case? What form should that be?
UI.
What about more complicated things? What if I had in R3 dx plus 2 dy minus 3 dz star? What would this be? Remember, I want to wedge it with the preimage of the Hodge star and get the volume form, which is dx wedge dy dz. Have to sit there and compute it. I think there's a way to actually compute this thing quickly. Unless you're doing like Hodge theory, it's not very obvious how that's done. But the nice thing about Hodge duality says that, I believe it's that every differential form will have a Hodge dual. And so the stars will align on everything. You may have some restriction to certain things when you're not talking about the basis forms. But you should be able to like distribute. I think it's linear.
What do we use it for?
This. Let's get the order of the symbols. If you're working in R3 and you get a function f, you sometimes in vector calculus will write an outlet f. And this is a vector field, right? You can rephrase this using exterior calculus as the following. You take the exterior derivative of the function and you chart it to get a vector field. So namely, if I take a function like this, f is just the radial function squared. Nabla f is going to be a vector, and it's going to be 2x, 2y, 2z. And this, of course, is just 2x del x plus 2y del y plus 2z del z. And you can see that this is just clearly this thing. Showing this, and then it distributes over the basis for the differential form, the basis covectors, and you get this thing. Okay. So that lets you rewrite the gradient. Also, I should say one more property about the exterior derivative. Anytime you have a form and you apply the exterior derivative to it, if you do it again, you get 0, no matter what. Okay. So that'll be used in the next fact. The curl of a vector field is defined this way. So if you have a vector field V, then the curl of V is, all right, so what is V? It's a section of the tangent bundle. In order to use Hodge star, I need to be in sections of the cotangent bundle, so I need to flat it first. And then I have a differential form. So I have a differential 2 form, actually, because I took a differential 1 form. I'm sorry, this is a differential 1 form. Then I take the exterior derivative of it, and I get a 2 form. And I need to get a 1 form so that I can sharpen it again to get a vector field. I think that's how it goes. So I want to get a 1 form first. So I take the star. So this is a 1 form. This is a 2 form. And then you star it, and you get a 1 form. And then you take the sharp, and you get a vector field. So that's the curl in R3. And you can, if you didn't want a Hodge star, you didn't have to. And you'll get something called a multi-vector instead of a 2 form. You'll get a 2 vector. And essentially the difference is Hodge duality will take you from having had 2 vectors, namely one like this and one like this. And then you get an orientation on the parallelogram that goes this way. And Hodge duality will say, okay, because it's right-handed, the normal is going to point this way, according to the right-hand rule. And this is what you get when you plug in the wedge product of these 2 vectors into the Hodge star. You get that thing, the normal vector to it. And then you can sharp it, and it takes you, should be saying, these are the sharps of differential forms that I'm working with exterior derivatives of. But then I sharp it to get this vector. I would have had a differential 1 form, and then I sharpen it to get that normal. That's why the curl, that's how you compute the curl. Now notice that the curl is the exterior derivative of a vector field in some sense. Right after flattening it. And the gradient of a function is the exterior derivative of that function. And that's a vector field. So if I take the curl of a gradient, that's the exterior derivative of an exterior derivative, which is 0. So automatically I get the rule that, chaining together these vector calculus idea, computations give me 0. And the same works for the divergence of a vector field, which is the same. So the divergence is star, D star V flat. That's of the vector. These only work in R3. I should say this works in R3. This divergence, I think, will work everywhere. And the gradient also works everywhere. And there's some exercises for actually calculating stuff like this and seeing how it mechanically works and getting an intuition for the Hodge star. The only other thing I wanted to do, but found kind of difficult, is an explanation of where Stokes' theorem comes from. Because if you try to pin down a proof for it, you need to either define something called chains, which we only do once we talk about simplicial homology, or you need to use some kind of visualization that they use in this Misner-Thorne-Wheeler gravitation book, which is a general relativity textbook. They have a nice visualization that I was trying to work out, but it's a little weird. I sent the notes, but we don't have time. We only have 5 minutes, so I'll go ahead and end here. And next week, I don't know what we're going to end up doing. We might end up doing Lie groups with PDE solving. But if anybody else wants to present something, your research, or topic you read about or something, that's fine.
Can you like tell me one more time, like you were hodging a differential form that has
Yes.
three terms? How would you solve that?
Okay, let's work in R4. I have X, let's work in R3. I don't know if that's visible, but try it. I want to wedge this. In fact, let's try wedging this. I want to take the Hodge star of that. So it should be something. I want to figure out what this is equal to. Okay, it should be a one form. Because I want to go up to, I'm working in R3. I'm Hodge starring a two form. It needs to be the complement in terms of dimension. So it should be a one form is what I get. Now, this is going to equal f of x, y, z, as a function, dx, because it's a one form, plus g dy plus h dz. And you can take this and make it satisfy the following equation. Take whatever you Hodge starred, wedge it with the Hodge star. Really, I should put parentheses around. Okay. Wedge it with the Hodge star, and you should get the volume form. Okay. And then you just take this, stuff it in here, and you solve for what the coefficient functions need to be. And naturally, in this case, this will end up just being negative dy. But in general, you should be able to solve this.